Okay, so welcome everyone. As I announced last week, so today there is the first, let's say, 40 minutes or so today. We won't have the traditional photogrammetry lecture, but the plan is to give you an introduction to how to write a research paper and telling you kind of how to write a good research report. It's not necessarily to be only a report, but it holds in general for any scientific document, for your bachelor thesis, for your master thesis. So whatever document you write in a scientific context, the suggestions that I will give here kind of help to improve that work. These are not kind of rules that you're not allowed to violate. That's definitely not the case. They are more a set of suggestions. And there are a lot of things when, if you look maybe to the papers I have written in the past, where I clearly don't follow these guidelines, or let's say follow 80% of those guidelines, but ignore 20% of those guidelines. That's completely fine, but it should be kind of an informed decision that you do if you kind of violate that. So sometimes you say, I can communicate my message better if I don't, or I'm not in line with the rules, so to say, that I'm going to present here. So the idea is to give an idea, what's the idea? So what's the motivation of writing a scientific document? How this is done? What kind of underlying structure such a document typically has? What are kind of a checklist that one should go through before finalizing such a document? And also introducing you in a few minutes in the end how how such papers or documents are typically evaluated. So some of the things that I provide here kind of hold more for papers that we submit to conferences or journals, but this is kind of 95% equivalent to what you write in a thesis, and of that, probably 80% of that holds for the report. So for the reports that you're writing here, there are a few things that you may do differently, but let's say if you object against them, be aware what you're doing. There may be a really good decision to say, I'm not following this single advice which is written here on that slide, but you should do that kind of being aware that you're kind of doing something which is non-standard. And so it's kind of the idea of this course here is to give you a couple of tools at hand so that writing reports will be easier in the future and you have a bigger impact of the work that you're doing, especially if you write down a thesis in the end, because it dramatically simplifies your life. There may be these also rules here which are not general rules for every discipline. This holds more for the engineering background, CS background. A lot of papers are written in that way. So if you look to a medical department or papers from a medical department, they may have a different structure, but that's kind of field dependent. But what I'm presenting here holds actually for most, let's say, things which come from the engineering disciplines. Okay, the first thing when you write a document is why are you going to write a document? So, and you should always have this kind of why in mind. Why is a pretty important keyword here. So, in general, the aim of writing a paper should always be to document the research findings that you generated. That means what kind of good ideas you had to come up with a solution or new solution to an existing problem or a new solution to a new problem and the results that your approach will, or how well does your approach perform on this type of problem. So that you document first for yourself or for your supervisor what you have done. And the second thing is to allow other people to replicate your results. Because it's also an important part of science is that you're not the only one who can solve this single problem, but you want to give tools to other people so that they're able to solve that problem as well. So it's important to document your findings and also to communicate with colleagues. Because what typically happens, you write a paper, you submit a paper to a conference, someone else is reading that, or maybe you put your thesis, your bachelor thesis on your own website, someone's downloading saying, hey, there's something interesting there, a problem that I'm also addressing, and then this person will come into contact with you, or you meet them at conference, at other events, and this is kind of a basis for a lot of discussions in their interaction with other people. So without having written such a document, you will not have that many scientific discussions with colleagues in the same field. Okay, so what is the potential impact that a paper can have? So what changes when you write a paper? So the first thing is you add something to science. So you have a new solution to a new problem, and this typically increases your reputation. So people will recognize that, and kind of the reputation level increases with hopefully paper by paper. Although, if you write a really bad paper, it actually can give some negative points on that reputation scale. Why it's in general important in academia? The first thing is it typically gives you better chances to get funding. So if you have proven that you did good research, it's easier to get funding for new research. There can be positions as studentische Hilfskräfte. This can be positions if you're planning to do a PhD. Or this calls as well if you leave academia and work towards industry, and industrial companies who are research oriented have an interest in having a person that is able to solve a certain kind of problem. So it actually increases or gives you better job opportunities, but always be aware if you write really bad documents, that's something which can harm you in the long run. Okay, so the next question is when should I write that paper? I mean, this is something which maybe doesn't hold that much for the report that you write because you're kind of forced to write a report, but you should always kind of have that in mind. Or the question is, should I start writing down what I did? The first thing is the results or the impact that my work is likely to obtain or the results that I obtain novel? So if you just replicate something what someone else already did, this can still be of value by saying that you replicate someone else's results, so you kind of prove that these results are fine. If 20 people have done that already before, this may not be the biggest contribution on Earth. And so there's some aspect of novelty in there. If you write a report, at least it's kind of novel for you. You may not be aware that this was a solution to a problem that you investigated. So this kind of novel to the scientific community doesn't hold really for the reports here. But this will, for example, hold for your master thesis. So if you go for a master thesis, sometimes it holds already for a bachelor thesis. It's kind of often somewhat borderline how much really novel a bachelor thesis is. But if you do a master thesis, in most of the cases, you have to specify what is new in here. So it's not sufficient to just replicate results, at least if you want to give a very good, you want to have a very good grade. Slightly related to that is how much related work did you actually look into? So related work is kind of scientific works that are already out there which address a related problem. So is there someone else who solved that problem already? Something we haven't discussed in the reports, but in the reports, at least in Photogrammetry 2, I'm going to expect that you also do some studies on what is out there in terms of related work. That means searching, typically today via Google or any other search engine or Google Scholar, but you can also do that via the library. See what's out there, who addressed a very similar problem, and describe what makes your approach different compared to the approaches which are out there already. So you need to document and specify how you are advancing the state of the art, relating your work to existing methods. That's also kind of a key element of a scientific document. Something we haven't addressed yet, but is something that will come in the Photogrammetry 2 course when we do the reports there. And the next thing is, unless you provided a nice mathematical proof of something for an existing problem, which doesn't happen that often, you typically have to show with experiments that the idea that you presented in your work is actually worth. So does it gain something in terms of accuracy of your method, in terms of robustness, in terms of easeability to use, in terms of required computational or memory requirements. So what is the advantage by using the technique that you propose? So if I want to convince you guys all sitting there that you should use my new fancy novel method, which may be painful to implement, you always ask yourself, why should I do that? And this why should be justified also by your experiments. That you have shown, let's say, that with a new technique, you can measure things better with a high accuracy, or you're less sensitive to outliers, to data association failures. Whatever it is, you have to show that in experimental evaluation. So far we discussed now kind of what are the things that should be in a paper, and what are the things, so a little bit talking about the why, and now the question goes, okay, how are we going to do that? If I now think I have implemented something nice, I have the feeling that this is novel, at least I'm not aware of any other method which solves it in the same way, how do I actually write that down? The first important thing is something that is often called a sexy start. So the important thing is, if someone grabs your work and reads through that, most of the people will stop reading after 5 to 10 sentences and say, ah, that's boring, put it aside. There's some other distraction. People don't read that much. So the most important thing is that in the beginning, you need to create interest for the reader or the reviewer, so the guy who evaluates your work or the person who in the end reads your paper when it gets accepted, and tell the person why it should read that. So the why is the most important thing and the thing which should come first, which actually doesn't only hold for scientific writing, holds for most writing or communication that you do. If you want to convince a group that you present something relevant, interesting, always start with why. That's kind of the thing which is, in this way, it's easier to convince the audience that you do something of relevance. So whenever you want to explain something, first answer the why question. Before you say something like what or how you do that. Why comes first. And also, especially in the very beginning of your work, don't really summarize what you've done. Try to sell that. Do advertising. So because the thing you want to achieve that the person says, oh, that's a really, really interesting work, and I'm going to read that now, and even if I'm distracted, I may come back to that because it sounded so interesting. It's the best thing which can happen to you, and where a majority of papers fails in that. So if you read the first, let's say, half page of a paper, and then you put the paper aside because you have to do something else, or you receive a phone call, how likely is that you will come back to that work? And so the important thing is to kind of sell your stuff in a good way and also convince the reader that what you're doing is important. And this typically happens in the abstract. So the abstract is kind of the short, which is sometimes called summary in German, which I don't think is the best translation for that. So I typically stick with the word abstract, which typically consists of 4 to 5 sentences. And most, or a lot of papers, at least good ones, follow kind of a certain structure. And the structure is kind of answer these 4 sentences. Sometimes these are 5 sentences, sometimes says a person, I want to put more emphasis on the what, or I want to put more emphasis on the why, or I may not want to explain the problem because it's so obvious, so I directly start with why, or typically why, the problem and why is typically done also in 1 sentence, and then I may spend a sentence more on aspect number 3. But these are 4 things that your abstract should cover. The first thing is state the problem. So what is the problem that you're investigating, and why is this a problem? This can be very simple, like mobile robots driving through the environment need to know where obstacles are in order to drive without collisions. It's a pretty clear statement. And then you continue with the next one. Why is this interesting? Because collision-free navigation is the key technology to build autonomous systems. And then you motivate it, if you have a paper which addresses a navigation problem, that this is something that is worth investigating. Or if you're going to present a new sensor, you say, doing high accurate measurements of whatever, buildings is important for several disciplines, for construction site, for evaluating how far construction sites are, for example, if you want to address that problem. And then you say, in this paper we present a new work that allows us to develop a more accurate sensor because this allows us to measure whatever, as accurate as before, but requiring only a 1/10 of the time to do that. So you really need to motivate your work. So you say, state the problem, say why it is interesting, so why should I continue to read that? So what is the gain that I, the reader, will get? And then you say what you're doing. So you say, what is my solution to that? This paper proposes a new algorithm to solve this and that problem. Or this paper presents a new sensor design which just costs a 1/10 of the price that a previous sensor system, for example, would cost. And then finally say what follows from that. So this technology enables us to, whatever, build more accurate maps than we could do that in the past, or get more accurate 3D reconstructions of buildings than it was possible before. You may say, this allows, whatever, new building technology to exploit this technique and do whatever this technology is useful for. And so the important thing is, does your abstract answer these 4 questions? And you typically should do that in that order. As I said, you may combine 1 and 2 into 1 sentence and then spend 2 sentences on aspect number 3 or number 4. That's all fine, but these 4 key things should actually be covered. So it's kind of the key element, having a good starting well into your paper and how to write a paper. Okay, what else? What's next? What should else be in the paper? The most important thing, and this is what most papers flag that get rejected at conferences, so typically it works like this, people submit papers to conferences or scientific documents that will be evaluated by a committee reading those papers, writing a report, and then based on the report, it says, oh, that's a good work, that's not so good, or not good enough, or has space for further improvements, and this paper will not make it. And one reason why a lot of papers fail is because they do not clearly state what the contribution of this work is. So what is the change that this paper generates for the reader, for the technology, for the field, and what do I learn when I actually read that and implement that technique? So what is the contribution? Why should I pay for that, listen to that, read that? Why not someone gives a talk and does not answer the why question, you may consider to leave after 20 minutes because they, I'm spending so much time here, why should I attend to that? So answering the why question is actually pretty important. Also, that's important when you think about the person who reviews your paper. So if you don't make it through the reviewing process, your paper will never get published. And reviewers and readers are often kind of lazy. So you read that paper, although you don't have time, but you have to do that. And so the best thing is to make it as easy as possible for the reader and provide a good message. So what's the message of your paper? What are the 2 or 3 sentences that you want to communicate? And this must be crystal clear, spelled out already in the beginning. So this is something which is typically done in the introduction. So if you go through the introduction of your work, it must be really clear without me having read the core method, that I know what at least the authors claim to be their contribution. Without that, the paper is very, very unlikely to make it. And the important thing is be very clear about that and spell that out explicitly. So it also is a matter of nationality often. So what's the background of the person, from which country they come from. If they spell out things very precisely, or if they use a kind of hidden form, using a lot of passive voice, and letting the author the reader kind of guess what the contribution is. At this point, this is not the way to do that. Be explicit as possible what your new technique allows you to do. So whatever, being able to design those features and use this classification method, we are able to recognize these digits with an accuracy which was not possible before. No one else addressed this problem in this way by, for example, using our great new features, using our great new classification algorithm. And so the key contribution of this work is this and this and that. So you can actually skim through papers, and often you find a paragraph on the first page, at least in the perfect case, and the paragraph starts with the contribution of this work is. Just skim for that paragraph. So if you're an experienced reader, you skim for that, and if you don't find it, you start with a very bad prior about that work. Okay, what else should be there? You should discuss related work, what I said before. So whenever you talk about scientific findings and scientific progress, you should write how this relates to existing methods. Again, this is something which we haven't done in the report so far, but this is something which is also a process which needs to be learned, and I expect that for next term, when writing a report, that you also investigate, let's say, look to at least through Google search, to the 10 most related papers out there, at least try to understand them, at least to some degree, and say, this paper is different because they address the problem which is, whatever, handwritten character recognition. But I'm doing something else. I'm doing whatever typewriter-based character recognition. And there are so many works trying to address typewriter recognition, but they rely on a different assumption. Or our work makes less assumptions about the input and still performs similarly, or with a similar performance. So actually have a large reference section. So discuss what other people are doing. That's kind of important to also give you, to emphasize your contribution, what your work is. If you list the 10 or 20 most similar approaches and say, but compared to work number 1, we are more general. Compared to work number 2, we are more robust. With respect to work number 3, we are faster. So if you can differentiate between different approaches, that's a big plus because it emphasizes your contribution. So what are the relevant techniques that you used, and kind of what I phrase sometimes as non-obvious theoretical results? So what do I learn from a theoretic point of view when reading this work, which is not extremely obvious? Although you typically have to say, if someone writes a paper, this person investigated a lot of time understanding the problem, so they may think something is obvious, although it may not be obvious for the reader. So you may even repeat something which you think is kind of obvious, but don't report the really, really basic stuff. Pictures often help, especially if it's a more complex system consisting of, let's say, multiple components. Pictures or diagrams that help the reader to understand what's going on are extremely helpful. Makes a paper nicer to read and allows you to kind of explain something with images which can be sometimes easier explained compared to words. Although the images are typically less precise, but if I first have seen the image and kind of already get an understanding what you're trying to communicate in the paper, then going through the text is sometimes easier or often easier to grasp. So we now have, after the introduction, we have related work and a reference section, an important element. We talked about kind of a method that we also want to say that let's say, what's the theoretical advantage that we have done. We may describe that in a way that we have something also visually appealing. And the next important step is the experimental evaluation beside the core method, description of the method, of course. So we need to convince the reader that the method we presented is also useful. So how does it behave with real-world data? When taking my new sensor out and getting new data in the real world, how does my sensor perform? Is it really as good as I described it to be? And so if I make a statement that my whatever sensor device measures 100 times more accurate than an existing technology, I need to have experiments that back up that claim. So measuring, for example, the same object with the traditional sensor in my new device and showing that it is 100 times more accurate, or whatever measure I'm going to take. So the important thing is that the claims that one does in the paper actually back up with the experimental evaluation. You should also at some point in time acknowledge the limitation of your method. If you only write, this is the best possible work, it is better than anything out there, it's very unlikely. Typically you may have relaxed one of the assumption, or you perform better because you made more assumption about your input, and something to explicitly state. So what breaks your method? In which situations it's unlikely to work very well. Something which is very important. And typically in the end, you kind of wrap up what you have done, you draw your conclusions, so you also describe what's the output of your experiment. So not only describe, in the plot number 8, we see the performance of the different methods. Really interpret the results and give your interpretation what these results mean. That one method is, for example, more accurate, or performs better in this setting. And give an idea on what can be next. So any paper, any thesis that you write will have this structure. So this is kind of the structure that you typically find in any work. So you start with an abstract, then you talk about the introduction, where you introduce to the problem, then you describe what's out there. So sometimes the related work sits actually here in the end. So this is a little bit of a design decision, a freedom that you have. If you put it in the beginning here, then this you typically do if you have an approach where you can present quite well kind of the general idea and then describe how this relates to other methods. If it's very technical and you need to know what's going on here before you can describe how your method differentiates from others, you may move it after the experimental evaluation. Then in a thesis you may add another chapter in here which says whatever basic techniques or things I just use in this technique, but you want to explain it so that others understand the thesis as one document. In the paper, that's not that often the case. Then you start with the approach. And the approach is a variable for describing with up to whatever 6 words what makes your method special. What's the key thing that you're trying to communicate. Then you present your experimental evaluation, the conclusion together with an outlook, and then the literature that you cited. So this in the end is just kind of the citations, the references to the existing techniques that you're doing. And in order to give you a concrete example, what I want to do now is there's one paper which is a very old paper. It's actually older than my research time in research actually started. But it's one of the papers which is a very early paper, but it's, at least from the robotics perspective, but it does all these points extremely well. And so it's if you read the paper and say, hey, this is a really, really nice work, it's sometimes worth going back and trying to analyze the structure of this work in order to identify what the authors did in order to make it a good work. So it's a good representative for a paper that is of high quality and which addresses a lot of the aspects that I've actually shown here. And just have some screenshots from the paper in order to try to illustrate what I've said here with more concrete examples. Okay, so the abstract. If you can, this is the abstract of the paper, and what the abstract should do, what we had said before, we should write one statement about the problem in general and the why. We should tell what this paper is about, so what are we addressing. We describe how we actually solve a problem, at least sketch it with one sentence, emphasize what is new or what is better, and say what's the impact of that. So why is this approach is better than what we've done before. Okay, so the first statement, write something about the problem in general, is actually the first sentence of this paper over here. So which says that, in this case, autonomous mobile robots need very reliable navigation capabilities in order to operate unattended for long periods of time. So the problem that is done here is navigation. The problem is autonomy, so unattended over long periods of time, and reliability. So these are the things that we are going to address, the important keywords in this abstract. And then the paper tells what the paper is about. The paper reports on first results of a research program that uses partially observable Markov models to robustly track robots' localization in an office environment and to direct its goal-oriented actions. So we know that we have an approach that is able to estimate the pose of a robot, so it localizes the robot in indoor environments. We even have an idea on how it's doing that by using partially observable Markov models, which is a special kind of probabilistic model. And besides estimating just where the robot is, it also is able to generate actions that are goal-directed. That means that guide the robot, for example, to a goal location. Then the next thing is it describes in more detail how it solved the problem. The approach explicitly maintains a probability distribution over possible locations of the robot, taking into account various sources of uncertainty, including approximate knowledge of the environment and actuator and sensor uncertainty. So it tells us which methodology or this framework it uses, using probability theory basically, in order to solve these problems. And then we describe kind of what is new, what makes it better, to emphasize our contribution. A novel feature of our approach is that is its integration of topological map information with approximate metric inference. Something the authors claim as their main novelty, so they're able to integrate metric information as well as topological information. So information about neighborhoods, in this case of places, as well as metric maps of the environment. And we demonstrated the robustness of this approach in controlling an actual indoor mobile robot navigating indoors. So they give an idea on why they think their approach is robust and how they evaluated that. And with this abstract, which follows a very, very clear structure, it's very similar to the first 4 bullets that I explained before, we're actually able to guide the reader through the paper and also giving the reader what the reader in the perfect case expects. That after the abstract has a pretty good idea on what's going on, at least on an abstract level, if it's worth continue reading, or if you should just dump the paper and not continue to read that. The next thing which comes is the introduction. So the introduction should start with the motivation, explain the why. It should, again, tell what the paper is about, of course, in more detail than the abstract compared to the abstract, and explains what makes this work relevant and novel. And we actually find those things in the abstract, so in the introduction. So this is kind of more or less the introduction, so this is the part where the abstract was sitting. The first part, so I won't read all of that, describes why the paper is important. So it provides a concrete motivation, of course extended compared to the abstract, why this, so it basically answers the why question. And then it says what has been done so far and how the authors are going to extend that by telling what the paper is about. So it's this part over here and this part over here. And then it finally describes what makes this approach relevant and gives more details on what the key contributions of this approach actually is. Sometimes you find something like sentences about the potential structure, so how the paper organized. This is typically not needed if you follow the standard approach. So if you start with your abstract, introduction, related work, main approach, experimental evaluation, and conclusion, you don't need a section like this. So this is something which at least I agree can typically be completely dropped because it doesn't add any key knowledge to the paper unless you violate this structure. So if you think you have a good reason to violate this structure and not use this structure, you may consider to explain that. This also holds for a report that you write. If you violate this structure that I present in the beginning, let the reader know about what your structure is. You may comment even on that with one sentence why you think it's better, although this is typically not done, but you should have a good reason for doing that. It's easier kind of to stick with the rules, but you don't have to apply the rules exactly if you think that doesn't help, but do that consciousness. In the related work, the important thing is that you put your paper into the scientific context, so relate it to the current state of the art and say what other people are doing. So that's kind of the related work section over here. And again, it tells in several places how the method relates to other and explain what the work of the others are in this field. So how have other researchers addressed this problem? Because it's quite unlikely that you are the first on earth who addresses such a problem. You may describe for every paper, which is the perfect case, which is typically not what you're going to do, otherwise the section would be too long and you wouldn't meet the page limit, to describe how your method differs compared to existing methods. In the perfect case, you do this, or you should do that for at least a few papers, the most relevant ones. You typically cannot do that for all papers, although the more space you have, the more you may exploit that. And also something which is kind of important in the end is that you typically summarize with one or two sentences in the end how you're going to advance the state of the art. So after you've discussed what's out there, let's say you describe the 4 key leading sensing technologies that are out there, they're currently used, and then you explain briefly with 1 or 2 sentences what the key highlights of your sensing technology are, which are better than these 4 existing methods. So kind of that in case the reviewer or the reader has kind of overlooked what your contribution was in the beginning, at least has 1 or 2 sentences to actually be reminded of that and wrap that up. Also citations. So in this paper you see kind of the things here in brackets, like whatever, some sentences, some statements, and then Kuipers and Boone 1988, that's a reference to a work. And if you go to the citations in the end of the paper, we find the name of the authors. So that was whatever I said before, Ben Kuipers, should be sitting somewhere here, Kuipers, which tells you where you find this work. So the name of the authors, the title of the work, the conference or the journal where it was published, and typically the year or maybe the pages even. And doing these things, selecting which works to cite, is also something which is sometimes a delicate choice for several reasons. So the first thing is you want to give a good overview about methods which are out there and methods that you think are important and address the same problem. By saying these are important things, you don't say it explicitly, but if you don't list someone who does something very relevant and this person may be your reviewer, he may be not amused about that because that means that you regard him as not as relevant, or he may interpret it like that. So be aware of whom you cite. You should, on the one hand side, also cite novel work, although of course the dates are 1994, 1991, but this is just because this paper is an old paper, to show that you don't only cite works that are 10 or 15 years old, because it may mean that you're actually addressing an outdated problem, a problem that has already been solved. So make sure you cite also novel papers in here. Then you should cite what the relevant conferences are of the target audience that you're expecting. So you need to know that which community you're going to meet. You make sure you address this community by also referencing to their works. There are other things, some old stuff you may cite, and the also important thing is what people sometimes fail to do is limit the number of self-citations. So don't talk always how great you are. You can relate to the key approaches where one of your authors is also an author, but you should actually substantially limit that to a certain number, or small number of so-called self-citations. Okay, now we are done. Now we come to the core part. We have the abstract, we have the introduction, we have the related work and the citations. And now we come to the technical part. What should the technical part do? What are the goals of the technical part? So the first thing is, you want to describe the work that you have done to others. In the ideal case, you do it in a way that others can re-implement your approach or at least replicate your results. Or both. Actually, replicating the results may even be harder than re-implementing it. That depends on the approach. So this is a key goal. There should be a technical documentation of what you have done that allows others to replicate that. That should be the clear goal of what you're doing. If no one else is able to replicate your result, it's first pretty frustrating for others, and second, people may claim in the end that what you report is not right, that you simply lied when writing that work, something you would like to avoid. In order to introduce this work in the technical section, you may describe some of the foundations which are necessary to understand that work. So you may wrap up with a few words how a camera works. If you present a new sensor which is based on camera technology, you may repeat with a few sentences what are the basic principles of the camera, and the model, or the basic mathematical model that you're using. You should do that also describing your approach with giving enough technical details. But that's kind of a critical thing, especially people who start writing papers. They get too technical too quickly. It should always be clear that you kind of start, or at least if you're not that experienced in writing papers, you start more on a high level describing what the individual components want to achieve, and then go deep. You don't want to go deep and hunch through all the small technical details without giving the reader to understand what the problem actually is. So you want to start on a high level and then go deep, but you need to make sure that you provide technical details that allow someone else to replicate the results. It's always good to also include the underlying mathematical equations, because with text you can be pretty verbose and avoid very concrete statements. If you put down the math, that's something which is typically more concrete, more precise, and people know exactly what you're doing. Of course, you should give an idea what concept the mathematical equations are describing, so that people have a chance to grasp it. But pure text is typically not precise enough. Again, we want to add figures, as we said before, or pictures, in order to make the approach or illustrate some of the concepts in order to make the approach easier to understand. And we want to mention the advantages of our approach, because we want to emphasize again why it is a good design decision what we are doing here. And you may describe the complexity, at least if you dramatically lower the complexity, or provide a more general method to make sure that what you do is not, for example, intractable to compute. And there are several aspects in the paper. So if you go through this paper again, there's certain things labeled with 2 and with 4. So 2 was, for example, describe the foundations. So the approach starts, the technical section starts here with explaining what this partially observable Markov model is that is used. So even if you don't exactly know what it is, by reading this first part over here until here, you should have a glimpse of what this mathematical model means and what the assumptions are behind that. You provide some of the underlying assumptions that are used in this framework, and that you are presenting a new way, for example, to efficiently estimate those probability distributions. You may use figures to illustrate what you're doing. So this presents the relations between the individual parts of the problem, and give the reader an idea on what kind of this topological map may be. There's places and distance between places, and what kind of Markov models are used in here in order to model the problem and say how perceptions and actions actually interact with each other. Yeah, then you again want to give some equations. You want to describe quite some technical details so that other people are actually able to reproduce the results. Again, some figures, and also describing in sufficient detail, especially at the important points which are non-standard, how you solve that problem, which may be non-trivial, so that others can actually replicate your results. Okay, we can kind of go through that or skip that a little bit. And One thing which I said before, which I wanted to mention is, especially if you're kind of new to scientific writing, start with this top-down approach. Give a global picture of what you want to communicate. And once the global picture is given, you can go deep in the individual components or aspects of your problem. Because if you don't do that, if you start providing all the details from the beginning on, the reader is very, very quickly lost. And you may start with, for example, on the top level, first explaining what the individual tasks are that you separate into components, that you now have, let's say, 3 components that you want to solve. For example, if you're in the classification problem, you have 3 problems. The first problem is how to get good training data. The second one may be how to get good features. And the third one is how to realize a good classification system from a technical perspective. So you broke that down into 3 components, and then you can describe the components with more details. So explain the concept for, let's say, the individual components like the classification system. What is the underlying math behind that? And then in the end, at the lowest bottom, provide the technical details that allows others to replicate your results. Okay, experimental section. Again, you want to describe what experiments have you conducted, why the experiments have been conducted. So in the perfect case, every block starts with a sentence, the first experiment is designed to show that, ... The second experiment is designed to show that, whatever. This new sensor is 100 times more accurate than existing technology. At the same time, it is easier to use than existing technology. Then it means you would have to, if you make these claims, you will have to provide 2 experiments, at least 2, one showing the accuracy and the other one showing the ease of use. If you don't do that, people will complain that you make claims which are not backed up by experimental evaluation. And that's hard to argue against that. There's something which can actually kill a good technical paper if the claims that it makes are not supported by the experiments. It always helps to compare your approach to other techniques. So if you have a baseline technique and your new great method, compare to what's out there. Like in the report, compare the nearest neighbor approach to the decision tree, for example. So make a comparison. Say which one is better, what are the advantages of the individual methods. Okay, there again, some examples from the paper was indicating the individual aspects, what has been done. And then we again have the conclusion. This is again a shorter part of the text. And the important thing is in the conclusion to describe again what you have done. Mention again what was novel, what you implemented, how you evaluated that, and the conclusion that you draw from this evaluation. So what is your interpretation of the experimental evaluation? You should have that in the experimental evaluation, but you want to kind of repeat the key elements in there. And you may even want to describe what's out there, what's next, how can we even improve that, what's future work, what haven't we addressed, which of the assumptions we have not addressed, but which we want to investigate in the future. So this was kind of the structure of a paper as well as for a thesis. So if you take a good bachelor thesis, master's thesis, PhD thesis, they will typically follow this structure. PhD thesis maybe not because it's too large, it's broken up into different chunks. But then these different chunks are typically organized in this way. You can see it's like a hierarchical approach. Okay, now we have described what we want to do and how we should describe that. Now some things about style. So these are things one should do or should not do in order to make the paper better readable and a stronger paper which is easier to access, which is more clearly written, and is more appealing to read. So the first thing is use strong verbs. So the example is, for example, replace a sentence like, we make use of categorization by we categorize. So you typically use a we form when you write that because you're typically multiple authors. Even if you're a single author, you typically use a we in academic writing. So make sure that you don't say, one solution to this problem could be to investigate how we may solve this system of linear equations. That's not what you want to read in a paper. You want to say, we solve this system of linear equation by whatever, sparse-Cholesky decomposition. So you want to make a clear statement how the problem is solved and not how one could solve that problem. Be very explicit, use very clear language when you write what you have done. It's also very helpful if you can provide examples. So if you want to express something which is difficult to understand, give a very short example and then say how the solution solves this example. Often it's useful to start with a small example and then kind of derive your way on how your method explain it based on the example. That typically helps when you read that. Don't use, unless again you have a really good reason to do that, parentheses, footnotes, bold characters, emphasization. So if you emphasize every second word or every one word per sentence, there's nothing to emphasize when something is really important. So don't use it too much. Use it only when you think the paper would be worse if I would not emphasize that, or my document would be worse if I don't emphasize this to make sure the person reads that. But again, the more you emphasize, the worse it gets. Spell checking. So if you use nearly every word processing system has a spell checker, simply use it. It's really annoying if you read a paper and there's a lot of mistakes. I also do a lot of mistakes, a lot of typos, grammar mistakes, especially if you write in a foreign language, or even if I write in German, that happens. But be aware of your spell checker and use it. There's no excuse to not do that. You can even do something more than a spell checker. You can do things like, there are tools like Academic Writing Check, which you can download here. It's a script, which you can run over your document, and it tells you, you failed. Use a lot of weak words. Here, use passive voice. You should use active voice. So this is done for English because most of the academic writing is in English. But whenever you have to write a scientific document, if it's in English, use the Academic Writing Check. Again, there are a lot of things that you may disagree with, but at least eliminate those where you don't care. If you make a very strong point that you want to have something in a certain way, do that. Also, learn something about what's called unbreakable spaces. If you have a space, you say whatever, figure 1, and you have a break, that figure, and the next line is 1, that it's really ugly. That's something you typically don't want. So learn about non-breaking spaces. You can set non-breaking spaces to make sure this is not broken up. Avoid negations. So you want to say, we are not going to avoid that. Don't use that. It's bad style. Another things, avoid useless acronyms. So there's a tendency in different fields to invent always new acronyms for their great approach. And yeah, that's typically something which is very bad. Especially don't use acronyms in the title or coin something new. That's not very good style. Avoid passive voice, as I said before. Use active voice, especially in English. But also the same holds for German. Passive voice is a very weak statement. Use active voice, say, we solve this, we do this. This is nice saying, every time you use passive voice, a kitten is killed by God, and you don't want to have too many kittens being killed. Okay, the other things are maybe, so the last thing may also be important. So make your paper easy to skim. So if you have a quick look, so just have 1 minute to look to the paper and see if it's interesting. I skim through the paper, and I want to be able to see if this is relevant. So use things to highlight the key advantages. For example, small itemization or bullet point list. You don't want to have 20 of them in your paper, but you may have one for the key elements so that it sticks out, and when you skim it, you can easily see what's going on. Words you can completely ignore, and this holds for what Academic Writing Check, for example, does. There are a lot of words like now, next, or things like very, quite, pretty. Our approach is quite good. Unser Ansatz ist ziemlich gut. This ziemlich should go away. It's nothing in academic writing. Either it is better, and then we show that through experimental evaluation, but these are words which people typically use in regular language or spoken language, but which should completely be abandoned from academic writing. Be precise and eliminate any doubt. Either you can make the statement, then you should make it, and you should make it very bold, or you cannot make the statement because it's not backed up by your approach to experiment, then you should dramatically avoid that. Code is something that people do. So there's no MATLAB, Java, C++, C code in papers. If you want to use code, what typically used is kind of pseudocode. So you see sometimes pseudocode in the lecture. So for example, this is a copy from one of the connected components algorithm. You can do that for one single key thing that is so essential that you want to be so precise how this is done to give someone the chance to replicate the results. Even if the person reads that paper 10 years later and Java is gone, for example, it doesn't exist anymore, or your favorite programming language. So it should be abstracted from the programming language. You can even have statements in there like whatever, find unlabeled foreground neighbors. Something which would be more difficult to write down algorithmically, but was very clear for the reader what's going on. So if you want to do that, you can use pseudocode, but also don't use it that often. You don't want to have 5 pseudocode algorithms in your paper. Maybe use it once for describing the core method. Comments about implementation. That's something you often do not find in regular papers, but that's something which you should put or can put into a technical report, into a so-called what's called a system paper when you describe a system. It's fine to comment on the implementation with a goal to simplify the life for others that want to replicate your results. This should be the only motivation for that. You can talk about your implementation, about certain details, how you have done stuff. The important thing is to separate that from the core method. So even if this implementation system or this programming language is dead after 10 years, which is not that unlikely or not in use anymore, your technical approach is still completely valid. People may, in 10 years, skip your implementation section. But that's something which, as I said, is typically not in papers unless it's a system paper or if you write technical reports. Technical report, that's often in there. Okay, now you have an idea on what should be in a paper. Next thing now is to go through a checklist. So once you're done, you have written all your document, take a checklist and check what's, if you're in line with all of that. The first thing is, do people outside your field, if you write that for the course, so someone's not participating in that course, but maybe studying the same subject that you're doing, understand the problem that you're addressing. I'm not yet talking about the approach itself. First, is the problem clear? Have you communicated clear what issue you're solving or what problem you're solving? And do people outside your field even have an idea how you can solve that? They don't need to perfectly understand that. If you show it to someone who's the approach what you've developed here to someone, whatever, who studies medicine, you can't expect that this person completely understands what's going on. Not blaming any medical students, but just because it's a different field. But at least they should have a glimpse or an idea what the problem is and on a very abstract level how you solve that. At the same point in time, you want to have people from your field, students you study with but who will not attend the course, they should be able to completely understand what's going on and they should even be able to re-implement your method from your description without any other help. If you give them your document, they should be able to replicate your results. In the perfect case, come up with the same plots that you generated, although I know that this is very unlikely to happen because you would have to provide too many details to get exactly the same plot. So this is quite unlikely, but it should be the goal to provide so many details that someone can actually at least overall replicate your results. So the important thing is the take-home message. Has someone else read your work before you submit it? If not, that's something to work on. Other things to check. Do the section headers have a clear statement? So if I read the section header, do I know what I'm going to expect? Do all my figures look nice? Or are these low-resolution screenshots done from the slides at a resolution of 200 by 200 pixels so that I can't recognize even the fonts in the images anymore? That's something you typically don't want to see. Things should be easy to read, should also look visually appealing. Again, you want to sell something. Page limits. If there's a page limit, like your report should not be longer than 7 pages, it should not be longer than 7 pages. There's no excuse for an 8th page. There are places where they simply don't consider those works, directly reject it. You're not in line with the style. That's not what you want to do. Is a layout looking nice? Do you have any windows or orphans? So windows and orphans are things like a paragraph starts at the bottom of the page and there's just one single line. Or the other way around, you have a long paragraph and there's just whatever 2 words on the next page. That's something which really looks ugly from a typographic point of view. You don't want that. You want to avoid that. This is something you do in the end. When your paper is completely done, it's completely written, you may do these optimizations in order to make it a nice and consistent document. Again, did you spell check? Said that before. If you explain something complex, do you have a step-by-step toy example? So very small example that everyone is able to understand that you can use to guide the person through that work. Do you motivate all your key steps in design decisions? If you say, I use this type of features because this is well suited for the problem at hand, give some more details on why you select that. Motivate your design choices. Every design choice should be clear why this is done. Check all the equations. It's incredible how many errors you find in equations. The reason is equations are very precise typically, so you can unambiguously or often spot errors and check if they are fine. Check if all terms are defined, are all variables defined in my equations. If not, that's something I should do. Is the notation consistent among equations, or on the first page and on the sixth page still the same? So is all that consistent? Something you can quickly check, which make the paper much, much easier to read. Okay, do you summarize your contribution in the beginning? Is your bibliography consistent? Spelling names of persons. If you cite someone, misspell his or her name, that kind of sucks. You should not do that. So go through it and see if you have a typo in names is also something which is important. Yeah, captions correct, so these are kind of more details. So, but what it basically means is be in line with the style. If you have a style gets provided to you, be in line with that. And when if you have figures in your report, there's no reason to have a figure in the report which is not referenced in the text. So if you have a figure 8 and figure 8 is never mentioned in the text, this figure should go. So every figure that you have should be referenced in the text. In figure 8, we see the result of our experiment that show that our method is 10 times more accurate than the existing method. If we don't mention a figure, throw it away. It's not going to stay in there. Okay, that's kind of something we skip. That's actually a recommendation that I give. So the first thing is submit PDF files, nothing else. If you use any other format, that really sucks. I'm even more pedantic and typically force people to use LaTeX. There's no reason to use Word, Pages, or similar. In terms of typesetting, they just suck. Use a proper typesetting system. LaTeX is one of those. We can create large documents, which maybe in the beginning you may spend a couple of days in getting used to that system, but it's an investment that will pay off dramatically. So writing is so much easier. You have all the references for free. So bibliography is automatically generated. All numbering of images is fine. It's not if you entered the 30th image, your Word crashes and all the references are gone. It's just a disaster. So simply don't do that. Use LaTeX. So far, we haven't enforced that. It's just a recommendation, but your thesis will probably be written in LaTeX, your bachelor thesis or master's thesis, and I recommend you, that's not the first document you should write in LaTeX. So my recommendation is use LaTeX. You only need to have a small number of features typically that you need. You typically have a style guide and you don't need to care about style at all. The system does it for you and does it typically much, much better than you would do that with hand tuning in your favorite word processing system, unless you study typography. Then you may be better, but that's, I guess, not the case for any one of us. Another recommendation, just to simplify your life, use a versioning system. So if you have people who don't use versioning systems, you typically find whatever, report 3, report 4, report Monday night, reports corrected by person X, Y, Z. You can do better. Use versioning system. There are versioning systems such as Subversion or SVN or JIT. JIT is the more kind of modern one these days. Which means all changes that you do to your document are tracked. You can say, I want to go back to the version I had Friday night, 8 p.m. And it's directly there. And you can even work collaboratively with other people on your report. Both can write at the same time. The system will merge everything into one consistent document unless you entered exactly the same line or paragraph. It does that better than you would do that. Believe me, it's easy to use. There are graphical user interfaces for that. So that's something, there's no excuse for saying, oh, I had that last week in the document and this thing is gone, I don't know where it is. You check out the version, check out minus revision yesterday and you have it. That's the way you should be doing that. Again, you need to get used to that, but it's Strongly, strongly recommended. Figures. Figures, as we say, they support us. They help us to make things better. But the question is, if I have nice, colorful images and they are very visually appealing, how do they look in a black-and-white printout? If I print the reports upstairs, I have a black-and-white printer. And can I see that? So it's a nice example. That's actually an example from my own paper. Talk about in kind of a classification or unsupervised clustering system on what the things can cluster. If you print it in black and white, it really sucks. We failed to use good colors that you could see in a black and white printout. Or having this red and green. Anyway, red and green is a bad design decisions because a lot of, especially the male part of the male population is red-green blind, so they cannot distinguish red and green very well. So depending on where you are, so you can see that was actually done by a red blind person because even here the legend has the wrong color, but that's a different story. If you print it in black and white, you cannot distinguish them. Don't do that. Fonts. You have these nice figures which show you some confusion matrices or some other distributions. The font are so small that you simply can't read them. If you can't read in a printout, you have to zoom into 800% in your Acrobat Reader or whatever skim or tool that you use in order to read these small numbers here. That should not happen. Again, that's from my paper, so I'm very happy to be able to blame that. That's not nice. We should not do that. Everyone makes mistakes. It's a long process to learn that, but make your papers look nice. How to set equations or text. So if you write something like this in a mathematical mode, this typically means E times F times F times I times C times I. If you want to say this is text, you have to tell your equation system that it may look like this. So you can see, for example, that here the F's are properly typeset. You have even the ligatures in here that these letters are together. Here, this is not the case. If you use this in equations, for example, as an index, like NF is an abbreviation for whatever number of effective particles, write it in this way because it's an abbreviation. It's not E times F or individual indices. Again, these are kind of small details, but you can see if people took care of that. Or, for example, it's very hard to see that on the slides, but there's a difference between hard spaces and regular spaces. If something is a name like Professor Albert Einstein, you have this dot in here, all text processes typically tend to break here. So you put a non-breaking space in here, which doesn't break, and typically they are a little bit smaller than regular spaces. So you can't see that here on the slide, but you typically see it in a printout. So eyes are very well trained to that. If you read a lot, you see those things, and type things suck. Screenshots. So you have, there's this great whatever image figure in one of the papers. So just make a screenshot and enter that. If you do that with a high resolution. You don't want to have those pictures in here, which really, really look like 2 minutes before the deadline, just all screenshot dumped in there in the paper, not even considered to maybe retype that or redo that. That's important. Okay, so that's it about the general comments. Just to give you an idea how typically the process works, how scientific documents are actually generated and evaluated. So typically, you write the paper and submit it. So like writing your report and submitting it. This is just the first line of the process of publishing something. So if you're in a conference, the paper will be sent out for review. This is also what happens here. So Susanne is correcting your submissions, or I may have a look to that as well. And this review actually reports back to you. So you get an evaluation. So you get comments on your work, what was good, what was bad, and how to improve your work. You get that also if you submit your paper to a scientific conference. Sometimes you have something which you call a rebuttal. This is your chance to give feedback to that. You say, this reviewer hasn't understood at all what I was trying to say. So you have the chance, sometimes for some events, to answer to those. And then the reviewers may also comment on that again. And then at some point in time, someone, which is typically the program chair if it's a conference, or it's the editor if it's a journal, makes a decision based on the reviews, potentially on your feedback, and says yes or no, accepted or rejected. And that's it. The reviews and the decisions sent out to the authors. It's actually quite similar to what happens here. Sometimes you have what's called a conditional accept. That means please revise your work or revise and resubmit, and then maybe we get it in, one chance more. If the paper is a negative decision, it's out. You have to try again from scratch at a different event typically. If the paper is accepted, you typically have a chance to revise your document, submit a final version, and then the document gets published. So that the process, which is the general process for scientific publishing, and actually how it fits also very well to the reports here are generated. So we don't have multiple reviewers at the moment, but that's also maybe something to investigate in next term, that everyone has to review the submission of the other students and give valuable feedback. It's also something we may try out if you're interested in that, to evaluate your peers, and of course by us as well, or an initial stage among each other, and then we do that. These are all things we may try out. Okay, that's actually it. So in the reviewing process, if you get feedback, look to the most critical statements. Even if you say, oh, this person hasn't understood at all what I wanted to say. This person is completely dumb. He has no idea what he has done. Maybe you're right to some degree, but typically it means you communicated badly. That means you failed to clearly describe what you have done and what the advancements of that are. Sometimes you get very concrete statements like, in equation 18 there's a mistake. Okay, you can fix that. Unless it's kind of a bad mistake which goes through all your implementation, that may be harder. But the important thing is, take into account the reviewer's comments. You may not agree with all of them. That's normally the case. You spend a lot of time in your work and you think what you did was good, and especially if you work for a year on a work and the work gets rejected, that's pretty frustrating. But that's part of the game, and typically there's something to improve. There may be also reviewers which are completely useless, but that's actually not too often the case, luckily, anymore. There's a nice video, which I can't show here for copyright reasons, but I encourage you to have a look to that. It's a kind of funny video making fun of the movie Der Untergang with subtitles on the reviewing process. Actually kind of fun. Other sources you may look into, kind of rules for paper writing or further reading. There's also books like The Elements of Style for general writing. That's something where every person who writes can actually benefit from. And if you want to read more, read those. Have a look to these resources. Again, some funny things, making jokes about how people write papers and things to avoid. Things should become pretty clear what's a joke in there and what's not. So in the end, we write papers to document what we have done and to advance the state of the art. This holds for technical reports, this holds for papers, this holds for a thesis. It's kind of your own contribution to the field to document your work and allow others to get the same success. This is a process which is ongoing, so you never start perfectly. It's a learning curve, and learning that is a painful process because failing really sucks. One invested a lot of time in that, I'm aware of that, but these guidelines, or at least my trial, to give you better tools at hand to write good papers. Talk to other people, get feedback from others before you submit. It's also one of the things I strongly suggest, because other people typically have a different view and can clearly say, yes, I think I can replicate your results, or I have no idea what you're talking about. This gives you a pretty good indicator that you may have to change something. As I said, there are maybe alternative ways for writing that. This is kind of styles which came up, at least in the engineering communities and also in the CS community. If you go to a different field, those recommendations may be different. But all in all, that's what helps you to write better papers. So the only goal in here is to give you tools at hand that allow you to improve writing and get better. There's nothing you do within a few months. It's something that you learn over several years, typically. And it doesn't help only for academic writing. It typically improves your writing in general if you're able to spell out things very clear so that there's no ambiguity anymore. Okay, that's it from my side about my guide on how to write things. Are there any questions about that at that moment? Anyone has an idea on how to start now if one needs to write a scientific document? Okay. Yeah? No, you don't need that. You can do that all locally. The only advantage if you have a server is if you collaborate with others. And you may have better backup system because not everything lies on the same hard drive. But SVN, as JIT, you can have local repositories and do everything locally. That's just SVN, SVN admin init or create and JIT init, and that's it. You have a local repository. Yeah. No, this works for every operating system. Although there are definitely graphical tools for that, And I'm not sure about the no, it should actually everything run under every operating system. And they're also kind of, if you want to host something, they're actually public services like GitHub, for example, or some other services where you at least can host open source code because it's often used for code development, but we also offer repositories for free. We also have a server set up here, so if one says, I really want to do that, we have a server which has also a nice graphical user interface which one could use for these activities. But that's something which is kind of, really it's just a tool for downloading. So I mean, I grew up with Subversion, so I can do Subversion a bit better, but kind of all the young guys now start with JIT, and you have to adapt to JIT, has some advantages of that. So if you start from scratch, use JIT, would be my recommendation. The things that you need for writing, you find in both systems. This doesn't hold only for text, so they're actually made for code. That's where they come from. And for code development, that's just you can't do without. You can't do good development without, because you can go back to revisions. Oh, I know something was working last week. Like SVN checkout -r last week. You get it, run it, and see what the difference is. So it's valuable tools. Anything else? Okay, so then let's make a 5-minute break, and then we're going to continue back with photogrammetry. Thanks.